Okay, so this video is going to describe some of the energy changes that typically occur as chemical reactions happen. So we're going to talk about how energy is actually either produced or released or absorbed when a chemical reaction happens. So before we get to that point, let's take a look first of all at some of the conditions that are needed for a chemical reaction to occur, right? So if I want two things to react together, logic would dictate that the reactants, the things that I want to react together, must come into contact with each other. They must collide. Now, in addition to the reactants colliding, in a lot of cases, especially when you deal with bigger and bigger molecules, those collisions must be in the right or in the proper orientation. So for example, if they collided in one orientation, that may not lead to a reaction as if they collided in a different orientation or alignment. And then the third criteria here is that those collisions, when they do happen in the right orientation, they must collide and provide enough energy to get the reaction going. And we call that the activation energy. Right? So in order for your chemical reaction to occur, your reactants have to come into contact with each other. They have to collide. They must collide in the right alignment or the right orientation. And then when they do collide in the right orientation, the energy of that collision must be enough to overcome our activation energy to get the reaction going. In lots of cases, we're going to see heat changes that accompany and energy changes that accompany chemical reactions. Heat is probably the most common energy change that we're going to encounter. Heat is just thermal energy. In a lot of cases, we're going to see two types of heat changes. We're going to see heat either being released or heat energy being absorbed as a chemical reaction happens. So let's take a look at the first example where heat is actually released. And when heat is released, we refer to that type of a reaction as an exo, meaning to the outside, thermic, meaning heat reaction, right? So in an exothermic reaction, heat energy is released to the surroundings. So the surroundings then would feel hot, for instance. And an example of that would be, for instance, if you burn something, right? Whether it's a Bunsen burner that you used or a match, right? That releases a bunch of not only heat energy, but also light energy. So in an exothermic reaction, we can see several things happen. So we know that heat is going to be released to the surroundings. And what that means then is that the products, whatever those products are going to have lower energy than the reactants. What this also means is that you can think of heat as a product. It's being produced. Right? And oftentimes sometimes you'll see the word heat being written on the product side of the reaction, or sometimes you'll see a unit of heat like kilojoules as a product. These different types of energy changes are often represented more concisely using what are known as energy diagrams. This is an example of an exothermic energy diagram. So on the y-axis, increasing here, we have our energy, and then on the x-axis, we have the progress of the reaction. So we start off with the reactants and we end up with the products. So what you'll notice is that the energy of the reactants here, where they start off, is higher than the energy of the products, right? So in other words, the products have lower energy than the reactants, which means that heat is going to be released or given off. So that would make it exothermic. The other thing that you'll notice here is that there isn't just a straight line that connects the energy of the reactants to the products. There is a hump or a hill that needs to be overcome, right? And the distance from where we start the reactants to the top of that hill or that hump, that represents our activation energy, right? This is the barrier that needs to be overcome, the energy that needs to be overcome to get the reaction going. Right, and in some cases that's pretty obvious to identify. In some cases it's not. So if you think of, lighting a match, for example, you take a match out of the matchbox, it's not going to spontaneously combust, right? What you actually have to do is to strike the match against the side of the matchbox. And what that does is it provides the collisions between the molecules, and it provides those collisions with enough energy to get over that hill or that barrier to get the reaction going. All right, so exothermic heat energy is released to the surroundings. The products have lower energy than the reactants, and you can think of heat as a product. The opposite of that is an endothermic reaction. And an endothermic reaction, heat energy is absorbed from the surroundings. And as a result of that, right, the surroundings would actually feel cooler as you take heat energy away. So in an endothermic reaction, essentially what's happening here is opposite to an exothermic reaction. So because heat is absorbed or needed, right, we can think of heat as a reactant. Right, and you'll see the word heat or some unit of heat energy like kilojoules on the reactant side of the equation. Because heat is absorbed, right, then the energy of the products is going to be higher. Than the energy of the reactants. All right, so if we look at our energy diagram, over here we see it looks different than the exothermic reaction. So in this case, the energy of the reactants are down here, and then the energy of the products are higher, right? So that difference in energy is the amount of heat energy that reaction actually absorbed. So energy of products greater than that of the reactants. Just as in the exothermic case, we see that there's not just a straight line that connects these two. We actually have to go through and overcome a huge energy barrier, or that hump, that activation energy that needs to be overcome. All right, so that would be an example of an endothermic reaction. Where you may see this happening would be, for instance, in a cold pack, right? If you injure your arm or your leg or something and you need one of these cold packs, if you've ever used that, you'll notice that you actually have to sort of squeeze and massage the cold pack to allow the reactants inside to combine. And as a result of that, it feels cooler. Well, what's happening is the reaction inside of the cold pack is actually absorbing heat from the surroundings. And because now the surroundings are your hands or your leg or your or your arm or whatever, it's going to pull heat away from that, and as a result, your arm or your leg is going to feel cooler. Okay, so we've seen how energy changes can accompany chemical reactions. Energy can be released in an exothermic reaction, or energy could be absorbed in an endothermic reaction. The next thing we'll take a look at is how quickly a reaction happens, and whether it's the same for all reactions. Right, so we refer to the speed of a reaction as the reaction rate. And as you probably can guess, not all reactions happen at the same rate or speed. Right, some reactions happen slowly. So some are slow. So for instance, like the rusting of iron, right, that doesn't happen in an instant. It takes several weeks or maybe months for rusting to happen. Whereas some are very, very fast, right? Some reactions are extremely fast. So for instance, explosions, right? That's kind of what makes them explosions, is the fact that you have this rapid expansion and production of gases. So how can the reaction rate or the speed be affected? Well, we can increase the speed or the rate a couple different ways. We can increase the amount of the reactants, right? So you have more things reacting, or more of the substances in the vicinity of each other. So that means the collisions are going to happen more frequently. And if the collisions happen more frequently, then the reaction is going to happen faster. Secondly, we could increase the temperature. All right, so you increase the temperature, you increase the kinetic energy, or the energy of motion of the particles. As they start moving around more frequently, they're going to collide more frequently, and as a result, the speed of the reaction is going to increase. The third thing we can do is to use something called a catalyst, right? And what a catalyst does is it speeds up the chemical reaction. But the other important aspect of it is that it is not used up. In other words, a catalyst is there at the beginning, and it's also there at the end. So the way that a catalyst works is actually quite simple. If this is our normal reaction, right, so this would be an exothermic reaction, what a catalyst does is it simply lowers the height, or that barrier through which we have to go through to get from the reactants to the products, right? So this here we can say is the catalyzed reaction. So it does so by lowering the activation energy. So as a result, more molecules then are going to be, or more of the particles, the reacting particles, are going to already have enough energy to overcome that lowered energy barrier, right? So for instead of having this huge barrier, this huge hill to overcome in the catalyzed reaction, we just have a much smaller hill to get by. Catalysts are very, very important things, and you find them all over the place. So for example, the enzymes in your body, right? Those catalyze pretty much every single reaction that's happening inside of you that allow you to survive and to exist and do the regular things you're able to do on a daily basis. So those are biological catalysts. And then you can also have things like the catalytic converter in your car, right? That is able to convert or catalyze the conversion of the gases that are produced from your engine. It converts them to less poisonous gases like nitrogen and carbon dioxide. All right, so we saw that there are three things that we can do to affect the reaction rate, right, or the speed. We can increase the temperature, which provides more collisions that'll allow us to get over that barrier or that activation energy. We can increase the amount of the reactants, which leads to more collision, or we can use a catalyst that lowers that hill or that activation energy.